Hello, this is Shoot Socrates. Welcome to video number 10 in my series for multivariable calculus, Math 5C at Pasadena City College. So in our last video, we computed exact values of double integrals using Fubini's theorem. And in this video, we are going to generalize that process by computing double integrals over regions which are not necessarily rectangles. Maybe you have triangles, maybe you have regions bounded by parabolas or the exponential functions or trig functions and so on, general kinds of regions. But first we're going to look at properties of double integrals, which are very similar to properties of the definite integral that we saw in basic calculus. So I will see you at page 10. All right, so these properties should not be any surprising to you. Suppose you have a rectangle from A to B and C to D as usual, and you have two continuous functions, f and g, continuous over that rectangle. Then the double integral of the sum, f plus g, can be broken up as the sum of the double integral of f over the rectangle plus g over the rectangle. Right? So we keep the domain, the rectangle stays the same, no bigger, no smaller. And all we do is that we break up the function into the two individual terms. Okay? So we do this all the time in calculus, right? So hopefully we can find this antiderivative easily and this antiderivative easily and so on. All right. And similarly, if you have a constant multiple, within your integral, then you can factor out that constant multiple. Okay, just don't do it if there's an x or a y hiding in there. Okay, that's not a constant. It has to be like a number like 5 or -3 and so on. Okay, so now let's go on to our main event. We're going to look at double integrals over general regions. So let me scoot this up a little bit. Perfect. I'm not blocking the view, but let me move up here anyway. So what we are going to do is we're going to consider double integrals of a continuous function over a domain D, which is not necessarily a rectangle. So we're replacing the symbol R with a more general symbol D. D for domain. Okay, kind of boring, right? But that's the letter we'll be using. So we will require that our domain is closed and bounded, okay? So basically that means that the domain includes all the points on its edges. There are no dotted lines, there are no holes. Every point on its edges is included in the domain. And we can trap D inside a big enough rectangle. Okay, in other words, it doesn't go off to infinity, whether x or y or both. Okay, it stays inside a small enough or a big enough rectangle. Okay, back in 5A, we saw these descriptions, and you might remember them once you see the picture. Okay, that will jog your memory. We're going to look at two special kinds of regions first. So a type 1 region has the form all points x, y, where x goes from A to B, and y is between two functions, a lower function g1 of x and an upper function g2 of x. Okay? A type 2 region is backwards. So you have all points x, y, where this time y is between two numbers, c and d, and x is between two functions. Okay, so you have a left function, h1 of y, and a right function, h2 of y. Okay, so let's take a look at the pictures. All right, so here are the kinds of pictures we'll be looking for. In a type 1 region, x goes from A to B, and y is between g1 of x below and g2 of x above. Okay, so we want a region which is between these two curves and between these two vertical lines. Okay, type 2 is flipped over. We're looking for a region where y is between c and d. So we have these horizontal boundaries, y equals c and y equals d, and x is between these two curves. Okay, so to the left is h1 of y, and to the right is some h2 of y. Okay, so it's kind of like you take this and then you flip it like this to get this kind of region. Okay, how do we compute the values of these double integrals once we have these kinds of regions? Okay, so we saw Fubini's theorems yesterday, and I used the plural because there were two equations. Okay, so there was one where dx is on the outside with matching x on the outer integral, and the limits are a and b. And in the inner integral, we have dy, and y went from c to d. Okay, so basically all we're changing is the notation in the inner interval. So instead of c and d, which is what we see over here, you have g1 of x below, right there, and g2 of x above. Okay, so how will this be different now from what we did in the last video? Okay, not that different actually. So we found this antiderivative, capital F of xy, with respect to y. Okay, so in other words, remember, if you take the partial derivative of this antiderivative with respect to y, keeping x a constant because x is the outer differential, then we should get our integrand, little f of xy. Okay, so in the last video, in this antiderivative, we plugged in d first, and then c, and then subtracted the value at c from the value at d. Okay, and that made y completely disappear, and so only x remains. But if you plug in functions, these functions instead of constants, y will still disappear, and only x is going to remain. All right, so once again, after we compute the inner integral, what we get for the outer integral will only be a function of x. Okay, let me also point out that in this setup, notice that there are constants on the outer integral. Okay, there could also be constants in here, but you should never have variables on an outer integral. Okay, this is going to be very important because very soon we're going to look at triple integrals. Okay, so we will notice the same pattern. We are going to have one more integral inside, but on the outermost integral, we can only have constants for our limits. Okay, so please keep that in mind. So for a type 2 region, we obviously have it backwards. This time, dy is the differential in the outer integral, and in the outer interval, okay, we have the interval from c to d. Okay, again, we only see constants on the outer limits. Okay, and in the inner integral, we have dx as our differential. Our lower limit is the left function, x equals h1 of y, and the upper limit is x equals h2 of y. Okay, so this time when we compute it, we look for an antiderivative. Maybe we should use a different letter, capital G of xy, where the partial derivative of g with respect to x should be this integrand, the same integrand, f of xy. Okay, so keeping y constant, we get the derivative of our proposed antiderivative, and we should get our integrand function over here. Sometimes it's possible to express a region either as a type 1 or a type 2. We have two choices. And when that happens, we call the a simple region. I'll give you an example in a little bit. Now, can every region be expressed as either a type 1 or a type 2? Not necessarily both. Unfortunately, no. Okay, so the worst case scenario that we're going to look at are domains where you will have to chop it up into 2 or more pieces so that you will get regions which are only type 1 or type 2. Okay, or maybe both. Okay, so when this happens, we will say that D is the union of, let's say, 2 regions. Okay, this is like level 2. Right, so that U there stands for union. Remember, the union of 2 sets. Okay, but of course, when we divide a region into subregions, they can only overlap at the edges. Okay, so yeah, basically no double dipping. All right, they can only intersect at their edges. Okay, so when this happens, we have one more property added to the other 2 properties, which are still valid in this general scenario, where the double integral of our function over the whole domain is the sum of the integral of the function over d1 and the integral of the function over d2. Okay, so this might sound like something you saw in basic calculus. Okay, the integral from a to b plus the integral from b to c is the same as the integral from a to c. Okay, so you just add up their contributions to each other. So let's go to Scientific Notebook and I will show you an example. So this was our example in the last video where we have this function and this rectangle. We went from 0 to pi over 6 and 0 to pi over 4. So what I'm going to do in today's example is I'm going to keep the function, but I'm going to change the domain. Okay, we're going to turn it into a triangle. All right, so let's scoot on down. And here is our example for Fubini's theorem over a general region. Find the exact value of the double integral, same function, over D, where D is the triangular region with vertices 0, pi over 6, let's call that point A, pi over 3, 0, call that point B, and pi over 2, pi over 6, let's call that point C. Okay, so from here, let's take a little pause and go to GeoGebra. We'll revisit this function, and we're going to draw this domain. Okay, so I'll see you there in a second. Right, I'm going to start with the domain. So A will be the point 0, pi over 6, over 6. All right, there is point A. Ta-da! B will be the point pi over 3, 0. There it is. And C will be the point pi over 2, pi over 6. Okay, so I chose these points. Okay, so notice that the coordinates are, of course, fractions of pi, but also C has the same y coordinate as A. All right, they all have different x coordinates. Okay, let's draw the domain. So for that, we'll need a triangle. So, oh, you know what? I can use escape. I can use the polygon command. Polygon A, comma, B, comma, C. All right, so there we go. Boom. Okay, so nice. We have this domain, and we are now going to see if this is a type 1 or a type 2 domain. Okay, get out of the way. There we go. Okay, so how do we decide if it's a type 1 or a type 2 or both or neither? Okay, that would be sad. Right, so type 1, we scan left to right, and we see if we have a function below and a function above. Okay, so to do that in GeoGebra, okay, we're going to draw pseudo vectors. Okay, so we're going to scan this picture and we're going to shoot arrows from low to high. Okay, and if I had a steady hand, those should be perfectly vertical arrows, like so and like so. Okay, so what's happening so far? We are entering the region at this line segment from A to B, and we are exiting it at this horizontal line. Okay, that's good. But once we cross the point B and we keep shooting arrows, we're not done yet. Okay, the idea here is to pretend that we're scanning the entire region. Okay, if you ever had an MRI or a CAT scan, okay, so that machine is going through your body, sending rays through you. So it's kind of like what we're doing. We're sending arrows through this region, and they're vertical arrows. Okay, so once we cross point B, though, the entry point, or the curve where we enter the region, is now this line segment from B to C. Okay, we exit at the same horizontal line. Okay, but what this tells us is that if we want to establish or write this out as a type 1 integral, we will have to do the D1 union D2 process. Okay, where we will have one triangle here on the left that stops at B. Okay, so it will be basically triangle up to here. And then you have a second triangle. Okay, a left triangle and the right triangle. So that won't be very practical, okay, because, yeah, it looks like it's going to be twice the work. If you do two integrals, you have to work twice on it, okay? Granted, the antiderivatives will be the same, but still, let's see if we can express it as a type 2 region instead. Okay, so let's start over instead of erasing all of those vertical arrows. Here we have a fresh diagram, okay? So in the type 2 scan, the arrows will be, surprise, horizontal, and we're going to go from low to high. Okay, so let's start over here, and we will go vector and make a horizontal arrow like this. Okay, so we are entering the region along AB and exiting along BC. Okay, let's keep shooting those arrows. Left to right, and a couple more. Left to right, and left to right. Okay, are they all behaving in the same way? We are entering the region along AB and exiting along BC. Okay, should we be worried about the bottom? No, not exactly. Okay, and up here, yeah, we're still, yeah, basically following that horizontal line. Okay, so it will be best to express this double integral as a type 2. Okay, so we're going to go back to scientific notebook because our next job will be to find the equation of this line segment and this line segment. Once we do that, we can go back to GeoGebra, this time in 3 dimensions, and see what we are integrating. All right, so let's just say that the type 1 scan told us that we will have to break up this integral into 2 if we want to use type 1 integrals. Okay, but the type 2 scan said that this is already a type 2 region. Okay, so might as well express it as a type 2 integral. Okay, so the horizontal arrows enter the region along AB and exit along, that was BC. Yes, BC, correct. Okay, so we need to find the equations of these line segments. Okay, so this portion is going to be algebra. It's a good time for a review. Here are the 2 points, A, B, and here are B and C. Okay, so we have 2 line segments, and we need to find their equations. Notice that these 2 points are special. They're intercepts. Okay, this is our x-intercept. This is our y-intercept. Okay, so we can use the intercept form. We have x over pi over 3. So that is our denominator here. Might as well just steal that. Plus, this time we have y over pi over 6. That is equal to 1. Okay, so what do we have to do? We're doing a type 2. So we need an x equals a function of y on the left and x equals a function of y on the right. Okay, we're doing the left. The entry point is on the left edge. Okay, so we need to solve for x in terms of y. Okay, well, let's see. What do we have here? Let's simplify the left side a little bit. So we have 3x over pi, flip the fraction, and 6y over pi. Okay, flip the fraction, and then get rid of the pi, right? So we have just 3x and 6y and pi. Okay, so now solve for x. X is our, in our notation, h1 of y. And this will be 1/3. Isolate x on the left. 1/3 of pi minus 6, y. All right. And if you want to make it look a little bit nicer, I guess we can distribute and go pi over 3 minus 2y. Okay, so that's our left function. What about on the right? We have BC. Okay, that's an intercept. Unfortunately, that's not an intercept. Okay, so here's the algebra review. We will use the point-slope form of the equation of a line. Okay, you remember that? I hope so. If you don't, well, that's why we're reviewing. First, we have to compute the slope. Okay, change in y over change in x. Okay, what do we do? Okay, well, let's use c as our first point. So pi over 6 minus 0 over pi over 2 minus pi over 3. And no, that's not 9. That should be a 0. Okay. So, what's that? Ooh, fractions galore. So we got pi over 6, pi over 2 minus pi over 3, common denominator 6. So that's 3 pi over 6 minus 2 pi over 6. Is that right? And so, what do we get? Pi over 6 over... pi over 6 also. Wow. So therefore, the slope of BC is just 1. Okay, what does the point slope form look like? Okay, remember, it's like this. You have y minus y sub 0 equals the slope m times x minus x0. Okay, who are these x0 and y0? Pick any point. We have 2 choices. Okay, so whether we choose B or C, we should get exactly the same equation once we simplify them. Okay, so might as well use point B because it's simpler. So pick B to get, so y minus y0. y0 is 0. equals m1 times x minus x0, x minus pi over 3. Okay, so of course we get y equals x minus pi over 3. Scoot. Okay, so as before, we need to solve for x. So x equals y plus pi over 3. And this is our right curve. Okay, so this is our h2 of y. All right, excellent. So we have the equation of the entry curve and the exit curve. Okay, they're line segments, they're not exactly curve, but we'll say curve anyway, because in general, they could be curved. So how about let's go back to GeoGebra, this time in 3 dimensions, and we will plot these line segments, but no, if we look at it in 3 dimensions, we will get planes perpendicular to our xy plane. All right, so let's check in 2 dimensions that our answers are correct. So we had x equals pi over 3. And I apologize you don't see this right now, but you will. There it is. Pi over 3 minus 2y. And I'm going to type in the other one. X equals y plus pi over 3 over 3. And boom, there it is. Okay. There's the other line. Okay, so it looks like our 2 equations are correct. So we will go back now to 3 dimensions and we will look at our function and our domain of integration. Okay, luckily I hadn't erased our work from yesterday and our last video rather, which was yesterday actually. So we have the same function, but now our domain is different. Okay, so first thing we're going to do is we're going to enlarge the rectangle where we defined in the last video so that it will contain that triangle ABC. So it looks like along the x, we have to go as far as pi over 2. So we have to change this to pi over 2. And then y, we have to go up to pi over 6. So it's actually going to be shorter. It's a little bit shorter than pi over 4. That's going to be pi over 6. And, ooh, so there is our new function. Yeah, to me it really looks like a piece of cloth that's kind of fluttering in the wind, but notice that a lot of it is going to be below the xy plane. A lot of it, or ooh, it looks like maybe around half of it. Okay, so from above, it will still look like a rectangle because it's defined over a rectangle and it is continuous on that rectangle. Okay, what about our boundaries? Okay, so we had AB and BC, but we also have the top. Okay, so that top is just the horizontal line at pi over 6. Okay, which is, which we actually see right there. This is pi over 6. Okay, so how about let's start with that. Okay, so the top wall is y equals pi over 6. Okay, so there is yeah, there it is. Okay, so that is one wall of our domain. Okay, but we have 2 other walls. Okay, so we have x equals pi over 3 minus 2y. And we have x equals y plus pi over 3. Ooh, okay. So that is our solid, basically. Okay, so we're cutting the surface over here and over here. Is it mostly above or mostly below the xy plane? I think it's mostly below. Okay, so I wouldn't be surprised if the answer that we get finally is negative. Okay, so with a little bit of work, you can make the diagram that we have in the PDF, but that entails writing surfaces. Okay, so let's do the computations. All right, let's find the value of that double integral. All right, so here's the original problem, and here are our left and our right curves. Okay, so we want this. We will set it up as a type 2 integral. We're going to get this. So in type 2, the y values are on the outside. So we're going from, okay, so remember the triangle, the lowest value is at y equals 0. The highest value is at pi over 6. Okay, so y will go from 0 to pi over 6. Pi over 6. Okay, and dy is on the outside. Okay. On the inside, we will have, on the left, x is our h1 of y, so pi over 3 minus 2y. And on the top, we will have h2, which is y plus pi over 3. Okay, there we go. And of course, we have a dx on the inside, and our function is this. Okay, so that is the complete type 2 setup. Only one integral. If we did it by type 1, you're going to need to add 2 integrals. Okay, shall we get the antiderivative on the inside? We have a dx here. So we will integrate with respect to x. Consider 2y, y is a constant. Okay, so what's the antiderivative? I believe, okay, so we will use u equals 3x plus 2y. So du is 3dx, and dx is 1/3 du. Okay, so the antiderivative will be, we want an antiderivative for sine of u 1/3 du. So antiderivative for sine, negative cosine. So we will have negative 1/3 cosine of u, and u is 3x plus 2y. So we will have minus 1/3 cosine 3x plus 2y. So quick check, derivative cosine, negative sign will cancel with the negative. We're taking the derivative with respect to x. So the 3 goes out, cancels with the 1/3. We are left with sine of 3x plus 2y. Okay, excellent. So now we will need to plug in our upper and lower limit. So on the upper, we are going to get negative 1/3 cosine. This is our x. So it is the function y plus pi over 3. So replace. Okay. So we are going to get 3y plus pi. Okay. Distribute correctly. And, excuse me, that should be an equals. And simplify to 3y plus 2y is 5y. Okay, remember how we used the trig identity yesterday? Okay, so we have cosine 5y, cosine pi is -1, and then minus sine 5y, sine pi, but sine of pi is 0. So I believe that this is just going to be equal to 1/3 cosine of 5y without the pi, and it's going to be positive. Okay, ready for the lower. On the lower, we have pi over 2 minus 3y. So we have this, and plug in pi over 3 minus 2y over here for x. Okay, interesting. So this is going to be, scoot up a little bit. What do we have here? Distribute the 3. We're going to get pi, and then minus 6y, plus 2y. So that will be pi minus 4y. Okay, cool. So shall we play the same game? Cosine pi minus 4y is cosine pi cosine 4y. So cosine pi, that is our -1. And then that minus turns into a plus. Plus sine pi sine 4y, but it doesn't matter because sine of pi is 0. So we have -1 cosine of 4y. Okay? And so the -1/3 becomes positive 1/3. So 1/3 cosine of 4y. Okay? So I'm always nervous with these sorts of things because arithmetic. So you know what? Let's try this. 1/3 cosine 5. I was correct. Haha. And how about you? And 1/3 cosine. Oh, okay. So far, so good. All right. So now we subtract them. Okay? Kept the sign. So plug into the outer integral. Okay? So maybe I should put upper limit here and lower limit. Okay. So we are going to get now outer integral 0 to pi over 6, and we have evaluated the inner integral as we have the upper limit here minus the lower limit over here, which is that. Okay. All right, so we're back to basic calculus, and of course, we can factor out the 1/3. So we'll have 1/3 here, and then we'll get the antiderivatives. So cosine 5y, little u substitution, we are going to get 1/5. And sine or negative sine? I believe sine. Sine of 5y. Again, quick check, derivative of sine is positive cosine. Okay, and then we have minus, similarly, we are going to get 1/4 sine of 4y. So let's make that a 4 and a 4. Evaluated from y equals 0 to y equals pi over 6. Okay, does everything disappear at 0? Thank goodness, sine of 0 is 0. So all we have to worry about is the upper limit, pi over 6. So we got sine of 5 pi over 6. And 4 pi over 6 simplifies to 2 pi over 3. I do believe. Okay, excellent. So it's now just remembering our trig. So 5 pi over 6, second quadrant, the sign, I believe, is 1/2. Okay, positive? Yes, positive. Because we're in the second quadrant, the sign is positive. There. 2 pi over 3, still in the second quadrant, but this time the sign is, I believe, radical 3 over 2. Okay, so we have this, and that should be a radical 3. Totally radical. Radical 3 over 2. Okay, so it doesn't look like there's much we can do to combine those. 10 times 3, so I think we're going to get 1 over 30. And then minus 8 times 3, 24. Radical 3 over 24. Excellent. And is that the correct answer? Yes, that is the correct answer. Okay, so yeah, remember from the last video, okay, we can't have the labels in our integral, or Maple will not understand what the hell are you talking about here. So we do get the same answer. And is that positive or negative? It is, just slightly negative. Okay, so within that triangle, it is almost above the xy plane with the same volume as below the xy plane. Okay, so we can think of it again as a net signed volume, which is almost zero, actually. Yeah, so I also wanted to make sure that once we got here, our integral was correct, okay, because it is so easy to make a little arithmetic mistake here and there. And usually it's a negative sign, right? Right? Never happened to you, right? Right? Okay, great. I'm glad it all worked out. So I hope you enjoyed our video for today. And I will see you next time. What are we going to do next time? I think we're going to change order of integration, something, or are we going to do a volume? I think volume first, okay? So many things to do. So until then, enjoy the rest of your day. Bye.